Hello friends, I am Amir Nizami and today we are going to see one example from the buckling of the laminated composite plates. So basically buckling of the plates I haven't started yet, but today only we will see one example as one of my students have asked the query. So he is getting some problem in understanding the results from the JNReady book. So I will just show that how I have written that and how I will run the code Matlab code for that. So let me just see. So I have written one code for that and I have run. So I got the results here for the buckling of the laminated plates. I've used three theories: classical laminated plate theory, first order shear deformation theory, and reduced third order shear deformation theory. So let me see. This example is for the anti-symmetric cross-ply, that is 090 plate. So two layer cross-ply. This is for the 4 layer and this yellow one is for the 8 layer. So we can see here this is for the 2 layer plate, we are getting this much buckling load. Okay. And this is for the 4 layer and 8 layer. So we are getting this buckling load for the first order shear deformation. Then we will see for the anti-symmetric angle ply. Anti-symmetric angle ply is there 45 degree and minus 45 degree angle. So this is for the 2 layer, then this is for the 4 layer, and this one is for the 8 layer, and this is also for the first order shear deformation theory. Now this one is anti-symmetric cross ply using the classical plate theory. Okay, so this 2 layer is this one which is showing a constant throughout the thickness. Okay, so it is not varying as A by H ratio is varying. This result is not varying. Okay, for 4 layer we will see that okay it's almost 20 and it's also constant, and for the 8 layer it's shown here which is nearly 22 point something or 23, so it is also constant value. Okay, so this is for the anti-symmetric cross ply, means 090 and okay. And now this is also for the classical plate theory, using classical plate theory, but for anti-symmetric angle ply laminate. So for 2 layer it is up to 15 or 16, then nearly 36, 37 for the 4th layer, and we will see here that up to 41.16 for the 8th layer. So we can also notice that in classical plate theory, uh, it does not depend upon the A by H ratio. The value buckling load is constant throughout the thickness, A by H ratio. Now we will see this. So this is for the reduced third order shear deformation theory. Okay. So for 2 layer we are getting this results. For 4 layer this one and 8 layer this one. Okay. Similarly for this one was the for the cross ply, and this is for figure 8 is for the angle ply, 45 degree and minus 45 degree angle. Okay. So if it is 2 layer, then 45 minus 45, it is 4 layer, so 45 minus 45, 45 minus 45, and similarly this would be up to 8 layer ply. Now this one is shown for the anti-symmetric cross ply using all three theories: classical plate, first order shear deformation theory, and third order. So here we have compared all three results. So third order shear deformation theory, 2 layer, so which is here, this round one, and then first order shear deformation theory, 2 layer is this red one. So we can see from here that first order shear deformation theory and uh, third order shear deformation theory is just almost same and coinciding with each other, and this is for the constant is for classical plate theory. So we will see that up to A by H ratio of 30 or 40, uh, the results for the classical plate theory and the first order shear deformation theory and third order shear deformation theory is matching, okay, and are coinciding with each other. Okay. But as the A by H ratio decreases, okay, so we can see the classical plate theory is much away from the exact results. Okay, so we can see for the thick plate, we can say that classical plate theory do not work better, but first order shear deformation theory and third order shear deformation theory are giving better results, more accurate results. Okay. Similarly, for a four-layer plate, okay, so we will see this. This is for the four-layer plate, okay, and similarly for this green one is for the classical plate theory for four-layer plate. So these results we can see from here. So we can say that the results are close, and for the 8-layer laminate we have shown the results here. So for this anti-symmetric cross-ply laminate we have seen that classical plate theory is giving much further or much error up to A by H ratio 40, and then after that the results are close to the first order or third order shear deformation theory. And we can also say that as the number of lamina is increasing, for the 2-layer it is buckling load is much lesser, but as the lamina is increasing for 4-layer and 8-layer, the buckling load is also increasing. Okay. For the anti-symmetric angle-ply plate figure 10 also we can see the same pattern. Okay, but we can say that in anti-symmetric cross-ply laminate we are getting the buckling load for the 2-layer as up to 10. Okay, but here we can see for the 2-layer we are getting higher buckling load up to 15. Okay, similarly for 4-layer we are getting up to 20, but here for the 4-layer in the anti-symmetric angle-ply plate we are getting 35. Okay, and similarly here we are getting results up to 22, but here for the 8-layer plate, and here for the 8-layer plate we are getting the results up to 41.6. So we can say that we are having advantage in anti-symmetric angle-ply plate here. For the buckling load we are getting a higher buckling load, so that a higher load would be required to buckle the plates. Okay. Thank you.